Hello again, this is Bruce Nielsen. Today we're going to talk about the early history of artificial intelligence and really the history prior to the invention of the term artificial intelligence. And it's really going to be a primer on propositional logic is what we're really going to be covering. So let's jump into it. So first of all, just a kind of shout out to my podcast. This idea came from my podcast, the Theory of Anything podcast, which is a podcast about artificial intelligence, human intelligence, things like that, kind of the search for artificial general intelligence. It's available on Spotify. And on that show, we've talked a lot about this idea of who was the first artificial intelligence or artificial general intelligence researcher. And I've argued that it was actually the early philosophers, Aristotle in particular. You might even be able to count Plato before Aristotle. So I'm going to explain why I feel that way about it. So let's kind of take a look at this timeline and what we're going to be talking about here. So here we have a timeline of early history of artificial intelligence. And I'm going to argue that it starts back as far as Aristotle at 350 BC. Then really we're going to be concentrating on certain nodes on the line here. In particular, the nodes that are going to be in bold here are the ones that we're going to be the most interested in. So starting with Aristotle way back in 350 BC, then we're going to eventually talk about probability theory, Thomas Bayes, Gottlob Frege, George Boole, and leading up to the first artificial intelligence conference that was in 1956. So today we're going to talk primarily about propositional logic. So we're going to be concentrating on Aristotle, George Boole, and Gottlob Frege. So let's start with Aristotle, as far back as 350 BC. We have a quote from Aristotle in Prior Analytics, his work Prior Analytics. He says, "A syllogism is discourse in which certain things being stated, something other than what is stated follows of necessity from their being so." So, for example, famously, we have the idea all human beings are mortal. We have another idea, Socrates is a human being. Therefore, that's what the line means. We can conclude that Socrates is a mortal. So we're just simply following the logic of the situation. This is what he called a syllogism. This is one of the early uses of logic way back in time. And it's what it eventually developed into Boolean logic and propositional logic and other kinds of logic from there. So if we were to jump forward in time, we've got this guy, George Boole. He wrote living in the 19th century, he wrote a book called The Laws of Thought. This is in 1854. So now notice that this is where the idea of Boolean logic comes from, is from this book. Notice that he saw Boolean logic. We would think of it as related to computers today. There were no computers in the 19th century, obviously. So he saw this as the laws of thought. He thought of himself as trying to work out what human thought worked like. And he was trying to come up with an algebra that represented human thought. So surely he believed he was an artificial general intelligence researcher, and that was what he was working out. Now, we know that it didn't quite work out that way, that things turned out to be a lot more difficult than that to reach artificial general intelligence. But I do think we've got this long history of trying to work out how human beings think. And this really is what led to logic and probability theory and to what we would today call artificial intelligence. Even though artificial intelligence as of yet, has not been able to actually explain how humans think. There's still something missing in our theories. So this guy, Gottlob Frege, is probably the next one we're going to talk about. So in 1879, he published a book that had a German name, but the English translation would be A Formal Language for Pure Thought, modeled on that of arithmetic. Again, we can see how he thought he was researching artificial general intelligence, right? So what he published in that book is actually what today we would call propositional logic, which is going to be the basis for other types of logic that we talk about. So he would be considered kind of the father of propositional logic. Again, this is in the 19th century. And he expanded out on George Boole's work and brought together a more unified logic that we use today. So now there is one person I'm kind of skipping over that probably deserves mention, honorable mentions here, probably maybe more than honorable mentions here, but I totally skipped over Chrysippus. According to everything that I've read, he actually developed a logic 100 years after Aristotle that was more or less a complete version of propositional logic that we would normally wait until 1879 to give credit to Gottlob Frege for. So I'm not going to go into what he did, but I just wanted to do a shout out for the fact that actually propositional logic arguably existed a lot earlier than when we would normally date it. So now let's jump forward a little bit further in time to the first artificial intelligence conference. It was held at Dartmouth. It was July of 1956. And in that conference, a paper was read that had the first use of the term artificial intelligence. So again, we see how artificial intelligence was founded on this idea of trying to work out how humans think, of the idea of artificial, what today we would call artificial general intelligence. So the paper coining that term that was used in that conference was actually from a year before, August 1955. In that same conference, Newell and Simon showed off their famous logic theorist program at the same conference. And it is today considered the world's first artificial intelligence program. And it tried to work out logic theorems, basically, just an automated way of proving different logic theorems. So, and Simon, if I recall, he actually claimed that he had solved the mind-body problem when he wrote this program. So it's, again, interesting to see how there was this belief that they were onto artificial general intelligence, that they had figured out how humans think and how to automate and put into a program human thinking. So let's actually talk about what they actually did find. Obviously, it did not turn out to be equivalent to artificial general intelligence. We're still working on that today. But what they did find was something very important. So let's discuss propositional logic and how it really is foundational to a whole lot of things that we do today. So we start with this idea that you can have basic statements. They can be, so let's say have a statement just be P or Q or R or something along those lines, and they can either be true or they can be false. So for instance, P might mean it is raining, and Q might be I carry an umbrella. So when you see P, you don't break it down. You know that the whole statement has to be considered either true or false. Okay. So then we allow logical connectives. So I've got here the operators that I'm going to be working with. These are some of the most common ones that are the best to work with. But we've got not operator, and, or, an implies, and an equivalent operator. So I've got kind of listed out what the operators look like. So let's start with not. If P is true, then not P is false. And if P is false, then not P would be true. Just flips the Boolean value from true to false and vice versa. Okay. With the and operator, we say P and Q is true only if P is true and Q is true. As opposed to the or operator, where P or Q is true if at least one of P or Q is true. We have the implies operator. P implies Q. We might say P, if P then Q is another way we might say this. We say that P implies Q is false exactly when P is true and Q is false. Otherwise, it's true. Okay, I'll discuss that a little bit further why I worded it that way. Equivalent, P and Q are equivalent, is true only when P and Q share the same truth value, both true or false. Okay, so that would be if and only if, P, if and only if Q. So one way we tend to work these things out is through truth tables. If we want to work out implications in logic, in propositional logic, we'll actually create truth tables. So I've got some truth tables here. So obviously with P, it can be true or false. Not P inverses this, false and true. And then I've got each of the operators. So we've got P and Q and all the different possible combinations of true and false that P and Q can have. And then I'm actually listing out what the truth values are for each of those operators. So P and Q only P and Q being true at the same time gets a truth value. P or Q, all of them are true except if P and Q are false. P implies Q. Notice that it's true in all circumstances except when P is true and Q is false. And then P is equivalent to true is true when P and Q is true and is false when P and Q is false. Otherwise, it's false. So let's take some actual examples just to try to make sense of this. So let P be my cell phone is charging. So at any moment, either P is true or it is false. And not operator as if P equals my phone's charging, and if that's true, then not P would be equivalent to saying my phone is not charging. With the AND operator, we say let P is I have bread and Q is I have butter. Then P and Q would be I have bread and I have butter, which is true only if both of them is true. With the OR operator, we say let's have P be it is sunny and Q it is warm. Then P or Q is it is sunny or it is warm. With the implies operator, I press a button and the light turns on. So if P implies Q, then that would be that if I press the button, then the light turns on. Okay. Equivalent then would be the switch is up and the lights are on. Then P is equivalent to Q if it has to be the case that the switch is up and the lights are on. Otherwise, the whole statement is false. So now, even though propositional logic did not turn out to be exactly equivalent to human thought, it is interesting, though, that they were onto something that was very important to human creativity and human thought. Okay, there's a direct connection between what they discovered and how epistemology, the theory of knowledge, actually works. Okay, so to understand this, let's play with one of the rules. Modus ponens is this idea that if P is I am hungry is true, and if P implies Q, which is equivalent to saying if I'm hungry, I eat, because Q is I eat, and if that's true, then Q, I eat, must be true. So it makes sense, since if I'm hungry implies that I'm going to eat, and I know that I am hungry, and I know it's true that if I'm hungry, I eat, then it must be the case that I'm going to go eat right now, or I'm eating right now, let's say. So that would be modus ponens. Now, here's where things get interesting. There's something called modus tollens, okay? So it turns out you can actually learn something in the opposite direction. So if P implies Q is if it rains, the ground is wet, and if that statement is true, and we know that not Q is true, the ground is not wet, then we know that it must be the case that it is not raining, okay? So in this case, we're going the inverse way. It's still P implies Q, but we're taking a not Q, and that allows us to deduce not P, okay? This is actually, according to philosopher Karl Popper, this is the whole basis for how science works, the logic of science, as he put it. That's famously the name of his book. The Logic of Scientific Discovery is the name of his book. So there is, what they discovered with propositional logic and what they were working on, it was related to human thought, and it did have a relationship to human creativity and how we go about doing science, but something was missing. Okay, there was more to it that they haven't yet discovered. Now, let's talk about the laws of logic. Okay, so one thing is this is true for any forms of logic. These are patterns that must hold if we're doing propositional logic. So we have idempotence. So the idea here is repeating a statement doesn't change its meaning. So P and P is the same as saying P. P or P is the same as saying P. Commutativity. The order of the terms does not matter for and or. So P and Q is the same as Q and P or Q is the same as Q or P. Associativity, grouping doesn't affect the results with and or. So P and Q and R with the parentheses around P and Q is the same as putting the parentheses around Q and R. That's the same also for the OR operator. This next two are not as obvious. Those first two are pretty obvious, but the next one is distributivity. So and distributes over or and vice versa. So if I have P and in parentheses Q or R, that's equivalent to P and Q or P and R. Okay. Now, De Morgan's law, duality, is that the negation flips the logic in the connectives. So if I have not P and Q, that's equivalent to saying not P or not Q. Okay. So these are the basics of the laws of propositional logic. Now, let's actually talk about the idea of, is propositional logic universal? Is it complete? Okay, so it is. So I'm going to give you a quick proof that I thought was kind of fun and interesting here. So let's think of these as atoms of logic. There's really no such thing as an atom of logic, I suppose, but we're going to start with this idea of using and, or, and not, and just those. Can we get all the other operators, such as the implies or the equivalent or anything else we want to make up? Can we get those out of just and, or, and not? Okay, and in fact, we can. We don't even need or. We can actually just use a not and operator and we can get everything. But it's a lot easier to understand if I use and, or, and not and treat those as the atoms of logic. So I'm going to start with this idea, looking at this truth table here. So imagine four functions. So we have function one, the both function, which is equivalent to and A and B. We have function two, and only, which is A and not B. We have function three, B only, not A and B. And we have function four, neither, not A and not B. So we're going to take all the combinations of possible values for A and B in our table here. And notice that what we end up with when we take these functions is that we have a true value on the diagonals. Everything else is false. Okay. So each of these, we get exactly one truth value for each of these functions, and it represents every single possibility for every single combination of A and B that can possibly be, since we're held to exactly two values for Boolean logic. So we know that we're now covering every single possibility. Okay. So these are called min terms, by the way. So let's take a truth value for the implication function. So we have A and B, all the different possible values, and we've got the truth table for A implies B. Now notice here something that maybe requires a little bit of explanation. We've got this idea of you only get a false here if A is true and B is false. Okay, so think of it like it's like a promise or a guarantee. So what this says is if A is true, then B must also be true. So if A and B are both true, that promise is being kept. But if A is true and B is false, then this whole implication must be false. Okay. Now, why do we give it a truth value if A is false? Well, the idea here is that if A is false, then we consider this as holding, right? This implication still holds. It's just that if A was false, then it doesn't matter what the truth value is for B. Okay, so because of that, we assign a truth value if A is false regardless. Now, based on this, what we can do is we can think of the implication as being equivalent to saying not A or B. Notice that the truth values of A implies B is exactly equivalent to not A or B. Okay, so notice how we can translate the implication into nots and ors in this case. But let's see if we can make this a more general proof. Okay. So let's take our min terms here, and which of the min terms corresponds to the implication function? Okay, so we know that we've got exactly one truth value for each on the diagonals here. What we want to do is we want to take which functions, if we were to OR them together, would be equivalent to the implication function here. So we know that this is going to be F1, function 1, F3, and F4. Okay. Notice that we've got truth here, and we got it there, and we've got these two, and we got these two there. So we've got 1, 3, and 4. Okay. Now, thus, A implies B must be equivalent to function 1 or function 3 or function 4. Now, to put this in a different way, this is the same as saying A implies B is the same as A and B, or not A and B, or not A and not B. Now, when I put it into this form, where I'm using the different min terms, and I have only ands inside the parentheses and only ors outside the parentheses, this is called disjunctive normal form, DNF, okay? And it's universal. I can represent anything this way, and this is what I'm trying to prove here. So let's finish off our proof. So we've got this disjunctive normal form version of it. Now let's actually take the truth values. We're going to list those out, and sure enough, this is exactly equivalent to the implication function, as we just proved. Now, recall that the min terms cover every single possible combination of A and B, okay? So therefore, it must be the case that no matter what function we come up with, it must be possible to always present it in terms of a set of ors between min terms, which means that the min terms made up of ands and nots, and that combined with ors must be able to cover any single possible function we can come up with in propositional logic. Therefore, we know that and, or, and not are universal in propositional logic, and they can represent any other function that we can imagine in propositional logic. So now, of course, we've really only proved this for functions that have two inputs. But you can see how we could make min terms for any number of inputs. We could do three parameters, we could do 4 parameters, and you're going to always end up with some series of ands, and with every single not possible for the parameters, and it would start to exponentially explode the number of number of min terms that we would need. But it would still always come down to a set of min terms, exactly one truth value for each combination of ands, and then we would use those with ors to put together a function. So based on this, hopefully you can see why it's intuitive that you should be able to create any Boolean function out of just using min terms like this. Therefore, or and not are atoms of logic, and we can create any Boolean function out of just and, or not. And that's it for this video. Don't forget to like and subscribe, and we will continue this discussion next time. Thank you.